Alright, I'm going to start section 2.3 here, and I'm going to start out with a pre-calculus problem that's going to end up being real helpful for us when taking derivatives, and it's factoring out the lowest power. And it's going to be real helpful in cleaning up a big algebra mess here. So here in this problem we have x minus 1 to the negative 1 power times x squared plus 5x minus x minus 1 to the negative 2 power times 5x. So notice that you have an x minus 1 and x minus 1, so those are the common factors there. Now the lowest power between the two is the x minus 2, so that's what we're going to factor out. That's the lowest power. And we're going to go ahead and factor that out, x minus 1 to the negative 2. So what's going to happen is if I'm taking away a negative, so remember it's kind of like subtracting a negative. So if I have negative 1 exponent here, and I'm subtracting away negative 2, that's really adding 2. So it's going to change it into a x minus 1 to the first power. And then x squared plus 5x is just hanging out. Minus x minus 1, and it would be negative 2 minus negative 2, which would be x minus 1. The negative 2 minus negative 2 would be 0, and then times the 5x. So normally we're not going to write this in, but this is just to illustrate what's happening, because when we factor out the lowest power, this case x minus 1 to the negative 2, when we factor that out, it's not there. Well, it is there, but it's the 0 power, so it's just 1. So now what we'll do is we'll have to FOIL the first folks. So FOILing that out. X times x squared is x cubed. X times 5x is 5x squared. Minus 1 times x squared is minus x squared. Minus 1 times 5x is negative 5x. And then over here, the x minus 1, that was just a 1. To the 0 power was a 1, so we just have 5x. And I almost forgot to write in the x minus 1 to the negative 2, so I just stuck it on the end. Normally we would put it in the, well, it doesn't matter, but normally I think we would put it in the front, which I'm going to go ahead and put it back in the front. I just got excited in the problem and forgot to write it. So here it comes back in the front, minus 1 to the negative 2 power. And then we're going to collect some like terms in there. So it'll be x cubed plus 4x squared minus 10x. And now that's not great, but it looks better than what it did originally. And then it'd be more easy. It would be more easy, easier to take. Maybe if we wanted to take the derivative of it again. My differential equations instructor always said things were more easy. He had a unique way of saying things. Alright. So something kind of helpful that we're going to use, some trig. Let's make sure this looks more like a 1. So if I draw a right triangle with an angle theta, the opposite will be the sine of theta, the adjacent will be the cosine theta, and the hypotenuse will be 1. If we use Pythagorean theorem, that's going to give us sine squared plus cosine squared. So the sum of the squares of the legs is equal to the sum of the hypotenuse. Let's try it again. The sum of the squares of the legs is equal to the square of the hypotenuse. And that's what I would want you to remember. If you can remember that one, then you can get the other ones. So if you can remember sine squared plus cosine squared is 1. You can get the other ones. 1 by dividing by sine squared, and sine squared divided by sine squared is 1. Cosine squared divided by sine squared is cotangent squared, and then 1 divided by sine squared is cosecant squared. And then if we divide by cosine squared theta, sine squared divided by cosine squared is tan squared. Cosine squared divided by cosine squared is 1, and then 1 divided by cosine squared, the secant. squared. So these are helpful things to know, but if you can just remember the first one, then you can easily get the other ones. All right. So we're going to look at the product rule, which says if I have a product of let's say I have two differentiable functions, f and g. If I multiply them together, they're going to be differentiable also. Now, it's not as nice as the sum or difference rule for differentiable functions. If I add two functions, and then if I add two differentiable functions, I can just take the derivative of each separate one and add them together. Product rule is a little bit trickier. So if I take the derivative of a product of differentiable functions, it's going to be f prime of x, g of x, plus f of x, g prime of x. So it's a little bit more complicated, and one way I like to try to remember it is it's the derivative of the first times the second plus the first times the derivative of the second, and it'll take a little bit of practice and you get the hang of it. So we're going to do a bit of a proof of this. So if I take the limit as h goes to 0 of f of x plus h times g of x plus h minus f of x g of x, so that's just using definition of limit. We're going to do a little sneaky trick here. We're going to add and subtract the same number, which isn't going to change anything. Okay, so we're going to rewrite, and then we're going to cleverly pick something to add and subtract. So in pink, we're going to subtract f of x g of x, f of x plus h g of x, and then we're going to add it. And you see, if we combine these, that's going to end up being 0. And then we're going to subtract f of x g of x. Okay, so in pink there, that doesn't do anything for us. If we add it back together, it's going to be what was originally here when we were taking the derivative. And what we're going to do is we're going to we got 4 terms, so we're going to group the first 2 and group the last 2. And the first 2 have an f of x plus h in common. So left over is g of x plus h times g of x all over h. Second 2 have a g of x in common, so we'll factor that out. We have an f of x plus h minus f of x all over h. Okay. Now, the f of x plus h times g of x plus h minus g of x all over h. This part here, that's going to be g prime of x, that's the derivative. F of x plus h is going to turn into just f of x. Differentiability implies continuity, so we have no problem with this just becoming f of x. Over here, f of x plus h minus f of x all over h, as we take the limit as h goes to 0, this is going to end up being f prime of x. And then g of x is just a constant there. Okay. So this becomes f of x g prime of x plus g of x f prime of x, which isn't quite what I said up at the beginning. I said it was f prime of x g of x plus f of x g prime of x. We can switch the order around. So we can make this f prime of x g of x. So we moved this second piece here. Doesn't matter, addition and multiplication are commutative, so we switch the order there. And then plus the f of x g prime of x. Okay, so that's your. You can use either form of the product rule here. You can say it's the first times the derivative of the second plus the second times the derivative of the first. It doesn't matter as long as you have f prime g of x and then f g prime as the sum, you'll be okay. Okay. The other one we're going to look at is the quotient rule, and it's going to employ a similar trick in its proof. So if we have f and g are differentiable functions, and g of x is not 0, so we can divide by 0, then the derivative is a bit more complicated than the product rule. So it's going to be the low function times the derivative of the high minus the high function times the derivative of the low function all over the low function squared. So if we take the derivative, it's going to be limit as h goes to 0, f of x plus h divided by g of x plus h minus f of x all over g of x all over h. And we have to do a little bit more work for this one. What I'm going to go ahead and do is I'm going to multiply by g of x plus h and g of x just to get rid of the fractions in the numerator. So we'll do that to the numerator and denominator of the big fraction. Oh, I also mentioned that g of x can't be 0. So when we do the fraction busting or clearing the fractions, we'll have f of x plus h times g of x. So the g of x plus h and the g of x plus h cancel when we distribute. And then we'll have minus f of x g of x plus h. So when I distribute to the second piece, the g of x will cancel out and I'll have f of x and g of x plus h. In the denominator it'll be g of x plus h, g of x, and then the h hanging out. And we're going to employ a similar trick as we did with the product rule. G of x plus h and g of x, that's just going to hang out, and that's going to end up turning into g of x squared in the denominator, this stuff right here, in a minute here. So f of x plus h g of x minus f of x g of x plus, I'm sorry, trick is adding f of x g of x to both, to adding and subtracting it. So minus f of x g of x plus f of x g of x minus f of x g of x plus h. No, we're okay. Sorry. I was thinking there was a mistake, but it's okay. Limit as h goes to 0, g of x plus h times g of x. And then we're going to group the first two, which have a g of x in common. So what we have left over is f of x plus h minus f of x all over h. The second two have an f of x in common. And then we have g of x minus g of x plus h minus g of x all over h. We also factored out a negative. So when we factored out the negative, that changed this into a negative and this into a positive. This sign right here became a positive. Okay. All right. So this f of x plus h minus f of x all over h, that's going to be f prime. And then we got the g of x there, so that's that's low times the derivative of the top minus the top, the f of x here, times the derivative of the bottom, and then this will be our bottom squared. Okay, so you're going to come on the last slide here to finish that up. So there's, as h goes to 0, the g of x plus h turns into just g of x. So we have g of x times g of x times the derivative of the top minus the top times the derivative of the bottom. And we'll go ahead and write that as low d high minus high d low all over low squared. So if you can remember low d high d low, that's the silly way of remembering the quotient rule. So low d high would be the low function times the derivative of the high function or the top function minus high d low. That'd be the high function times, or the top function times the derivative of the bottom function. And I think I have another video that will show some examples of taking derivatives using product and quotient rule.